Climate change adaptation refers to actions taken to reduce vulnerability and increase resilience to the physical impacts of a changing climate. Unlike mitigation, which seeks to reduce greenhouse gas emissions, adaptation focuses on managing the consequences of climate change that are already occurring or are expected in the future. Adaptation measures can include constructing flood defenses, improving water management systems, developing drought-resistant crops, strengthening infrastructure, and enhancing disaster preparedness. Effective adaptation requires consideration of local climate risks, socio-economic conditions, and long-term climate projections. Because climate impacts differ across regions, adaptation strategies must be tailored to specific geographic, environmental, and economic circumstances. A key consideration in adaptation planning is the risk of maladaptation, which occurs when actions intended to reduce climate vulnerability unintentionally increase risks or create new problems. For example, sea walls may protect one coastal area while increasing erosion in neighboring regions. Similarly, large-scale planting of non-native tree species may reduce biodiversity, increase susceptibility to pests, and disrupt local ecosystems. Adaptation effectiveness also varies among countries and communities depending on financial resources, governance quality, infrastructure, and institutional capacity. Wealthier nations generally possess greater adaptive capabilities, whereas developing countries often face higher vulnerability despite contributing less to historical greenhouse gas emissions. Mitigation refers to efforts aimed at reducing greenhouse gas emissions and limiting future climate change. Since the global energy system remains heavily dependent on fossil fuels, mitigation strategies focus on lowering carbon intensity and transitioning toward cleaner energy sources. Common approaches include expanding renewable energy generation, improving energy efficiency, electrifying transportation, reducing deforestation, enhancing carbon sequestration, and promoting sustainable industrial practices. Mitigation also involves policy instruments such as carbon taxes, emissions trading systems, and regulatory standards. Successful mitigation requires coordinated action across governments, businesses, investors, and consumers because emissions originate from multiple sectors throughout the global economy. Numerous technologies support climate change mitigation, each presenting distinct opportunities and challenges. Renewable energy technologies such as solar, wind, hydroelectric, and geothermal power can significantly reduce emissions from electricity generation. Electrification of transportation and industrial processes can further lower dependence on fossil fuels. Carbon capture, utilization, and storage technologies offer the potential to reduce emissions from hard-to-abate sectors, while negative emission approaches seek to remove carbon dioxide directly from the atmosphere. However, mitigation faces challenges including high investment costs, infrastructure requirements, technological limitations, political resistance, energy security concerns, and the need to balance economic development with emissions reduction objectives. Geoengineering represents a more controversial response to climate change and generally falls into two categories: carbon dioxide removal and solar radiation management. Carbon dioxide removal techniques include afforestation, bioenergy with carbon capture and storage, direct air capture, and enhanced weathering. Solar radiation management seeks to reduce incoming sunlight through methods such as stratospheric aerosol injection or cloud brightening. Geoengineering may provide supplementary tools for addressing climate risks, particularly if emissions reductions prove insufficient to meet climate goals. These technologies could potentially slow warming, reduce climate damages, and provide additional time for mitigation and adaptation efforts to take effect. Despite potential benefits, geoengineering presents significant scientific, ethical, governance, and environmental concerns. Many techniques remain unproven at large scales and may produce unintended consequences. Solar radiation management could alter precipitation patterns, affect ecosystems, and create geopolitical tensions regarding implementation and oversight. Carbon dioxide removal technologies often require substantial energy, land, water, and financial resources. There is also concern that reliance on geoengineering could weaken incentives for emissions reduction by creating a false sense of security. Consequently, Most climate experts view geoengineering as a potential supplement rather than a substitute for aggressive mitigation and adaptation strategies. Carbon budgets, national commitments, and emission scenarios provide frameworks for limiting future temperature increases. A carbon budget represents the cumulative amount of carbon dioxide that can be emitted while maintaining a specified probability of staying below a temperature threshold such as 1.5 degrees Celsius or 2 degrees Celsius above pre-industrial levels. Under the Paris Agreement, countries submit nationally determined contributions outlining emissions reduction commitments. Climate models evaluate alternative emissions scenarios and their associated warming outcomes. Achieving ambitious temperature targets requires rapid emissions reductions, attainment of net zero emissions during the second half of the century, and potentially significant levels of negative emissions. Delayed action increases the difficulty and cost of remaining within available carbon budgets.